Hey, good morning. Yesterday we started the exam preparation and we managed to get into until problem 5, that is finding internal loads inside a compound beam. So let's continue with that. And now we'll have the next problem, that is problem number 6. Okay, finding the moment of inertia is very critical for final exam, because directly or indirectly you will be asked to calculate the moment of inertia. So by itself, that is a um, kind of assessment question. Also, if you want to find out the internal stresses, that both type of internal stresses in beams, shear stress and bending moment, both of them, they depend on reversely on the second moment of inertia. So here we've been provided with a cross section. So with this cross section, um, how to find the moment of inertia. The first step is I have to consider a reference plane, and with this, my reference plane is, I mean, could be anywhere, but let me take my reference plane as shown here. Okay, so here I have divided the shapes into, there are two vertical sections above the reference. This is X is my reference plane, and one horizontal one, that is section 2, and the last one is the one at the bottom, 3. So with this, we would like to find the center of area for this cross section. So that is X, and we want to find this all right, my reference is at the bottom of the second shape. So this is 1, that is also 1, that is 2, and this one is 3. Okay, so first thing first, you want to find out the y bar. That is, there are two cross section A, so that is 2 times the area of this one, which is 25 by 100, 2 times and then plus multiply by the centroid of that with respect to the reference. The centroid is 50 from here, 25 from there, that is 75, is it? and then plus that of the second area. The total width of this one is 100, that is 325. And the thickness is 25, and the centroid of that one is 12.5. And that still we have to include the last shape. This is, the last shape is 100 multiplied by 25, that is 2,500, and the centroid of that one is the centroid of that is minus 50. And that's divided by sum of the areas. So if you calculate this one, that y bar is equal to 22.5 millimeter. And that makes sense because there are more area above the reference than below the reference. So you expect this one to be positive. And also we notice that the central piece, that's very bulky. So that dominates the centroid, bring the centroid close to the X center. So at this stage, all I need is just that y bar, and let's make some room for the rest of the calculations. Okay, so next we would like to make a table. These kind of problems are best solved by tables. So here we start with the segment. So how many segments are there? Segment 1, 2, 3. And what we are interested is the area of the segment. So the first segment, because it's repeating, and then there are two of them, the area is 50 by 100 or 25 by 100 by 2. That is the area of the first one. And then I would like to know, okay, in the question, it is asking the moment of inertia Ix prime about X prime axis. So this is X axis. What is the, well, if that is 22.5, the centroid of this shape is where? The centroid of this shape is 25 plus 50, that's 75. So 75 take away 22.5, that is 52.5. So 52.5, that is the distance between the centroid of the first shape and the x-axis. So this is D1. So that is DI. And then the next quantity we want to calculate, that is the centroid from the table. For the first shape, what is the centroid from the table? So that is I from the table. So let's call this x prime. That is 1/12 BH3. Because there are two of them, B is 25 plus 25, that is 50. And H is 100, so that is 100 cubed. And also we have to find the area of the shape multiplied by di squared. That is the penalty. The penalty term is 13.781 multiplied by 10 to the power of 6. And the unit for that is millimeter to the power of 4. So if I just calculate that Ix prime, the number I'm including that here, this is millimeter to the power of 4. That is 17.948 multiplied by 10 to the power of 6. That is for the first shape. We have to do the same for the second shape. For the second shape, the area is 325 and the thickness is 25. And what about the distance of the second shape with respect to here? So this distance is half of 25 is 12.5. So if I take away 22.5 from 12.5, that is 10. So here di is 10. And then with the I from the table, if I get the I from the table, that is 1/12. B is 325 and H is 25. And let's multiply the area by the square root of di. That is 0.8125 multiplied by 10 to the power of 6. And finally, let us write the result of that Ix prime here. That is 1.236 multiplied by 10 to the power of 6. And lastly is the shape below, the shape number 3. So area for that one is 25 multiplied by 100. And what about the distance? So here I've got 55 below the axis. So that 55 measures from here. That is D3. So D3 is 50 plus 22.5, that is 72.5. And what about the moment of inertia from the table? From the table, that is 1/12, and B is 25, H is 100. And let's multiply the area of the third shape by its distance squared, and the result is 13.14, 10 to the power of 6, and that is the product of the A by the, this is the penalty term, okay? So this is the penalty term. And just without the penalty from the table, the value is 15 point. Which one? 72.5. Negative. Well, because yeah, that's the distance between them. The distance is important. How far you have to shift this, above or below? Because you use D2A, it doesn't matter if that's negative or positive. But here, simply we want to know how much shift you are making, either down or up. Okay, the value for that is 22, 4, 10 to the power of 6. And you notice that here, since we wrote everything in a tabular form, it's easy to check the calculation and it's easy to add everything together. So from this table, all I have to do is I need to write this like that. The total I, that is 2 times I1 plus I2 plus I3, and I1 is 2 times x prime plus A1 D1 squared, and for the second one plus Ix2 prime plus A2 D2 squared plus Ix prime 3 plus A3 D3 squared. And by adding all this together, the total moment of inertia is 34.4 times 10 to the power of 6, and the unit is millimeter to the power of 4. So when you are calculating moment of inertia, either that has to be in terms of the meter. Meter is so big. So generally speaking, we write that in millimeter squared, and if the forces, the unit of the force is kept to Newton, everything else in the millimeter, the stress would be megapascal. Okay, so that is the entire solution. If you want to copy from the screen, I squared, I prime. That is what you get it from the table, without caring about the. I mean, I prime is from the table. You assume that this is a shape, right? You get it from the table. It's for rectangle I prime, if I understand your question correctly, this is B, this is H, right? That from the table with respect to the center, that is 1 over 12 BH3. Is that your question? Yeah, okay. In the exam, you have formula sheet, you have for primitive shapes like rectangle, triangle, circle. You can grab them from the table, but if that's an unusual shape, you have to calculate this based on the principles by integration. I go through some example of that. All right, I give you some example when we have to do the integration to find I. Is that, did I answer your question? Not sure if I understand it. All right, so let's go to next problem. The next problem is you have been given an unusual shape, and for this we want to calculate the moment of inertia about the y-axis. So let me show you this. Perhaps all right, here I want to find that about the y-axis. Okay, about the y-axis, the element which I'm choosing, my element should be parallel to the y-axis, all right? So here, I do need to have an element with the dx, that's the thickness. The distance from here to there, that is x, okay? And then what is that area? The area is, and then this parameter here is y. So my dA is y dx, and here that is x value, right? So from the principle, from the first principle, y is defined as the integral of x2 dA. And that integral should be taken over this area. This is the total area.
Are these revision classes also going to be uploaded on YouTube?
Say it again.
Are you also going to upload these revision classes on YouTube?
This one, yes, I'm recording them. I'm recording them here. It takes maybe, if I have time today, I would upload them, but definitely by end of week, you will access yesterday, today, and tomorrow also on YouTube. Okay, now, how do I include x over here? All right, so I mean, one might think that I need to find x before working this integration, but that's not true, because if I go with dA, let me write dA. So dA is y multiplied by dx. That is h by b cubed x3 multiplied by by dx. All right. All right. So that is my dA, and the thing is here I don't need to calculate x in terms of y. Why? Because I can change the domain of integral either between 0 to b or between 0 to h. 0 to h is when I have the expression in terms of y changing between 0 to b. As long as it scans the entire area, either horizontally or vertically, that does the calculation. You remember from calculus, there are two ways you can calculate this area. Either you take the element vertically and then the scan is horizontal, or you get the elements horizontally and the scan is vertical. So in this, we decided to scan the area by taking a vertical element, and the scan is from horizontal, from 0 to b. So in another word, if I plug that here, I would get I y is integral of h b cubed x cubed multiplied by x2, that's x5, and dx. So that is dA. That was the entire thing. This was dA. So that integral, because the scan is horizontal on dx, x is changing from 0 to b. All right. So you remember that integral from calculus. That is, the coefficient comes out. That is h by b cubed. And this is x6 by 6. And the variations are between b to 0. So this results in HB cubed, and that is B6 divided by 6 minus 0. So that can be simplified. B6, B3 you cancel or simplify, that is H B cubed by 6. All right, let's check the dimensions. From dimension point of view, does it make sense? The dimension of I should be L to the power of 4. B is length, H is length, so the dimensions, 6 doesn't have any dimensions. And also we were given the answer in the question sheet. The answer was, BH by 6. That's the answer. So two cases. If in the exam you are dealing with the standard shapes, you grab the I value from the table, and if that's a composite shape, you have to find how far that is from the centroid of the shape, and then applying the theorem of parallel axis, you calculate the penalty, add the penalty to the standard value. This is scenario number 1. Scenario number 2 is you'll be given an odd shape like this one. So here you have to start from the definition. Definition is if you are asked IY, that is a definition. If the question was what is IX? IX is integral of y to dA. And over there, possibly you would have taken element in a different direction, horizontal. Questions? Okay, when we are talking about the internal stresses, this is not always the beam that we are talking about. Sometimes you are interested in stress in an average sense. In average sense, generally speaking, is either a cross-section subjected to a uniform axial load, compression tension. In that case, you calculate the sigma, or that is a pin subjected to the shear, or a lap joint subjected to the shear. That is the force divided by the cross-sectional area of the tangent to the force. And next problem, problem number 8, that is asking about the average stress. So let's take that one. Any question with this one? Can we move on? All right, so I bring the next problem here. Let's read the question and understand this first. Now, let me explain. This is a chandelier which is suspended by 2 cables. The cables have different cross sections, and well, we could find the stresses inside each cable. And in an ideal case, both cables are under the same stress. If one of the cable is more stressed than the other one, you're wasting material. You know what I mean? In terms of sustainability, you don't want to use excessive material. Excessive material is when one of them is under stress, the other one is relaxed. But if both of them are under the same stress, that is the optimum design, because then you can control and put that stress below the limit. Every material has a limit. So for this material, the limit is 150 megapascal. We don't want either of the cables go above the 150 megapascal, but the reality is, if we do that, one of the cable would be far below 150, the other one is just below 150. And then the only way you can find this is to check the forces and the cross sections and see which stress is larger. That stress should not exceed 150. The other one is safe. So first step is you have to do the free body diagram. Questions. Are we going to be asked questions before the mid-semester? Yes or no? Free body diagram, there is no way you can just exclude it. So here, that is how I solve this problem. First is the free body diagram. So chandelier is, I don't know the mass of the chandelier. So the weight applied here, that would be mg, correct? And then that is force AB. That is the limit of the material. 150 megapascal is the limit of the material. All right. So make sure in the exam, just make drawing, make illustrations. Almost in every exam, I see a student just writing the numbers. Look, if you get something wrong, I need to see your free body diagram to give you a mark. And the chances, if your free body diagram is making sense, you get a big portion of the mark. But if you don't put any illustration, drawing, how can I? That's a very important step to solve any engineering problem. If you cannot visualize it, if you cannot present it, the chances are you won't be able to solve it. Please take this seriously. So that angle is 30 degrees, and this angle is 45 degrees. So how can I solve this? Either by resolving the forces into X and Y Cartesian, or because there are only three forces, maybe the best option is the method of triangle. So with the method of triangle, I start with the given force, which is mg, that is vertical. And from one end, I draw parallel to FAB. And from other end, I draw parallel to FBC. And as such, this one becomes FBC, this one becomes FAB. And what about the angles? Okay, so the angles are, this one is making a 45 degrees angle. This one is making a 30-degree angle. And that is 30, this is 60. And this is also 45. Correct? All right, so what rule should I use here? Cos rule or sine rule? To solve that triangle, should I use cos rule or sine rule? Sine rule, that is more convenient, and that is mg divided by sine 75 is equal to FBC divided by sine 60 is equal to FAB divided by sine 45. Okay, so two equations. From these two equations, easily the forces can be calculated. So, but these forces are calculated in terms of the mass. Mass, we don't know what is the maximum mass of the chandelier. That's the final thing we want to find. So if I write these forces, FAB and FBC, in terms of the mass of the chandelier, FAB is 7.181 M, and FBC is 8.795. Okay, even without solving the problem, can I say which one of these are more critical? No, I can't, because still these are just the forces. If you want to find the performance, you need three inputs. First is the force, second is the cross section, third is material or limit. So here that is just a force. How do I know about the area? So it says AB has a diameter of 3 millimeters. So DAB is 3 millimeter, and the diameter of BC, that is 4 millimeter.
Excuse me, sir. Can we do it by resolving the forces
To the area. That's a normal stress. These are normal stress.
Can you make the components of each force x and y and then do it?
Solving the free body diagram, yes, yes. But I thought that was easier this way. If you're more comfortable with Cartesian, you resolve the forces in x and y. That give you two equations, two unknown. You have to solve them at the same time. Yeah, you can do it that way. FAB. Where did I get this from? Okay, that's easy. Just let's pretend this one doesn't exist. Then you manipulate that expression. That is m times 9.8 divided by sine 75 is FAB divided by sine 45, which is root 2 over 2. Okay, and now here FAB is equal to, that is 1.7 multiplied by 98m divided by sine 75. So that coefficient is here. And you can do the same thing, ignoring the last one, just taking the 2, and I do it like that. All right, now the next thing is I have to find out the stress in each cable. What type of stress develops? Is this a shearing stress or normal stress? What type of stress develops inside each cable? Normal stress or shearing stress? Well, if the force is perpendicular to the cross section, or if your member tends to become longer or shorter, that's a normal stress. If the stress tends to shear the material, something like a scissor, like a lap joint, like a pin, so that's shearing stress. In this case, we're talking about the normal stress. So the normal stress inside AB, that is FAB divided by area of the AB. Area of the AB is pi by 4 and 3 squared, which is 9. And what about the normal stress inside BC? That is FBC divided pi by 4, 16. So if you plug the numbers, that becomes okay. So these can be simplified further. And if I set this one equal to, I keep the 9.8 and this one in kilogram, that is Newton. Everything else is in millimeters, so that is megapascal. Megapascal, that if I set that equal to 150 megapascal, So each one of these give me a mass. So they are not the same. So I have to keep the lower mass. That is more conservative, right? So from first calculation, according to AB, the mass is calculated to be 146, sorry, 7.64. And if I do the same thing with BC, the mass is calculated. This one gives me mass equal to 214.31. So which one should I? 147 is more conservative, right? Anyone needs this to be explained again, or is that understandable? Any question? Don't be shy if you want me to explain again. You know the limit, you know the forces, you know the areas. So each stress is calculated in terms of the mass. So assuming that each cable has reached the limit of 150, you can find out what mass caused at that limit. So inside BC, BC is stronger than AB. So the weaker point is AB. AB is going to break sooner. So you just account for that one. All right, next problem, again, that is a normal stress problem. Like I said, when it comes to internal stresses, that's not always to do with beams. Beams is a routine problem. You have to find the shear force diagram, bending moment diagram, and from that, finding the internal stresses. But if we are talking about the average stress, that is either normal average stress or average shearing stress. Next problem, that is problem number 9. Problem number 9. It's very similar to the previous problem. So again, to make a judgment regarding the performance, you need internal forces, you need the cross-sectional areas, and you need the limiting stress. All right, in this case, as long as both cables are under the same stress, that is enough. All right, so the question is, what is that equal stress is another question, but here you want to optimize, you want to make sure both cables are under the same risk. So how do we do that? Again, you have to find out the tension inside each cable. So that is my free body diagram. If I take the entire thing as an envelope, there will be a force of mg acting down. So I know that hook is taking mg. Therefore, in the second step, if my envelope is just around here, I have to cut through the cable. And then my free body diagram becomes like this one. mg upward, FAB, and this one is FAC. And mg, that is 2 megagram. 2 megagram is a very stupid way of units. That is 2 times 10 to the power of 6 gram, which is 2 times 10 kilogram, which is 2 tons. So W is, if I want to keep that in Newton, that is 2000 G. That is in Newton. So how do I solve that free body diagram? Again, that is almost 20,000 Newton. Almost 20,000 Newton. 2 megagram. That is 10 power 6 gram, 2000 kilogram. 2000 kilogram. Okay, so here the angles are 30 degrees here, and this one is 40 degrees, 45 degrees. All right. Again, this free body diagram can be solved by
In your free body diagram, why did you direct it mg upwards?
because you could do this like that, Rook. That is how you can interpret it. If I don't separate that and then just I cut the cable, this is my internal forces. I don't care, right? So this is mg, and that is mg. Okay, and then this is action reaction. Look, how much if you don't separate, if you don't cut the cables. So that is free body diagram is what? This is an envelope. This is my envelope, right? So my envelope is separated from the universe only from the hook. So hook, the internal force should be exposed, and that is a free body diagram like so. So this is hook. I just released that from the hook. So for hook to hold this, the only force here is mg. So the hook is taking mg. And then when you are cutting, the second free body diagram is when you are cutting through the, so now my envelope is like that. So the second run, my envelope is through this. So I'm cutting through the cables. The cables are, the internal forces are exposed, and also the hook action reaction. Okay, so now the solution is up to you. You either can do with the Cartesian resolving the forces, solving two equations, two unknown, or you can construct a triangle and use the sine law. So let's do the sine law again.
Can you do it?
Yeah, I do it with that one. So with the Cartesian, you would get net forces horizontally equal to 0. That is FAB minus sine 30 plus FAC sine 45 is equal to 0. All right, is that obvious? The second one is the net forces vertically equal to 0, and that is 2000 G. That is almost 20,000 Newton. Minus FAB cos 30 minus FAC cos 45 equal to 0. So now you have two equations, two unknown in terms of A, B, A, C. From one equation, you find FAB and substitute that in the second equation, and that give you back substitution, give you the forces. If you solve these two free body diagrams, these two simultaneous equations, what you find is FAB is equal to 14362 0.83 Newton, and that is in tension. And also you find FBC, or sorry, AC. So FAC is 10156.06 Newton, and that is also in tension. All right, now just okay, AC, diameter of the AC is 10 millimeter. Okay, but you don't know the diameter of AB. So we want to calculate the diameter of AB. If AC is 10 millimeter, so you have to write this like that. Sigma AB, you want to have sigma AB equal to sigma AC. So that is all right. So if I solve that equation, how many unknowns are here? The only unknown is DAB. Okay, that gives me a, I simply cancel pi by 4, and then DAB squared. That is equal to 14362.83 multiplied by 100 divided by 1015606. So from here, the next step, I need to take root of both sides. So DAB is 11.9 millimeter. All right, next problem is somehow tricky. Yep. Just bear with me a second. So do you want me to explain this again, or you want me to explain it again?
When you wrote the values for the forces in y direction, you also put the forces in x direction with it.
Did I? So with the X, there are only FAB and FAC, but in the Y direction, that's the second equation. That is 20,000 is upward positive, and then the components of these two forces on the y-axis.
But you made a bracket with math-wise.
That bracket means two equation, two unknown.
Oh, okay.
Two simultaneous
But
equation.
it still lies on the
Yeah, that's two simultaneous equation you have to solve. Let me know when you finished.
so you can
Yep, all right. So next problem is a designer has proposed a new design for a bike seat. Oops, what happened? Okay, a designer has proposed a new design. So in that way, the bike seat is attached to the frame by using a hinge at point C and also a telescopic damper, which is BD. Can you visualize that? So BD is like a damper and C is a hinge. All right. The question is, I need to find out the forces inside the structure, but in the first look, it seems to me the gray beam is not solvable, because if there are two pins, every pin has two reactions. So two reactions, or four reactions, and you only can handle three. So how can we avoid this problem? There is a little hint, if you notice, that you can solve the problem. A little trick. What can you tell me about the BD? What kind of member? Is that a beam or is that a bar? BD. Porty, BD is this a beam or bar? Why do you see beam? Is this gonna change the radius of the direction? Will it become shorter or longer? Something that can only shorten or length become longer, that is a bar. It's not a beam. Beam is when the radius of curvature changes. Just imagine if that deforms, the gray is a beam because the radius of curvature changes. But with the BD, that's a telescopic arm. Yeah, telescopic can get shorter and longer. It won't bend. If a telescopic arm bends, that's a wrong design. Telescopic is a hydraulic system, is only designed to take the axial load. Okay, so why that is important? Beam or bar? Why should we care? BC being a bar. A bar is a two-force member, right? It can only take the force in an axial direction. So that way, I know at B, the direction of the force I know, but the magnitude I don't. So one magnitude at B, two unknown at C. The free body diagram for the beam only has three unknowns, not four unknowns. All right? Do you want me to explain again? Is that clear? Explain again? Okay. So what happens if I release that one external force? The reactions should be exposed at B and C. So two forces here, two forces here, four forces. You cancel. But given that you know this one is a bar, the two force member, the two force member can only take a force along this axis. So now I come back with this free body diagram. There are not four unknowns anymore. Two here. With that, I know the direction of the force, but I don't know the magnitude. One magnitude, two unknowns, three unknowns altogether. So that is now solvable. But what are we
You're not going to cut it from B.
from BD? From BD, we know that this is a bar.
You will cut it while doing the free body diagram.
Depends. The problem is asking about what? Okay, you want to you want to find forces entirely. You want to solve the entire beam, B and C.
I'm just asking you, what would be the approach?
What would the approach? Okay, the approach is now I release the seat. Okay, so by releasing the seat, I have to find the forces at B and C. Once I have the forces, then the question reduces to a pin under shear. Okay, so that is
So
how.
you're not going to find the force at B because you're not going to cut it from there.
No, we just simply let me do the free body diagram for you. Just bear with me. I do the free body diagram for you. So now my free body diagram would look like this one. Okay, this is an external force. The weight is ignored, and that one is a compressive force, which I'm going to resolve into two components because that is with a 60-degree with the horizon, right? So then if that is under tension, if I assume that the forces are under tension, there is one vertical force here, and here also there are. So that is Cy Cx. So what is BD BDY? BDY is BD times cos sine 60. And this one is BD cos 60. Okay? Now, to find out the BD, I take the rotation with respect to the C. So the net rotation with respect to the C equal to 0. So rotation due to the BD sine 30, that is multiplied by 100. That is in a negative rotation, minus BD sine 60. The arm of rotation is 100. And the rotation due to the BD cos 60, that passes through C. No, that doesn't pass. It is 30 mil below. So that is in a negative rotation, minus BD cos 60 times 10. And the only positive rotation is due to the P. That is plus P multiplied by 400. So from here, um, we have to assume that P is a given value. All right, so we at this stage we find the BD in terms of the force P, or the force is being given 1,500 newtons. So P is 1,500. And then we can solve the equation by taking rotation with respect to the B and two other equations. Eventually, you find out Cx and Cy. Okay, Cx is 2952.68 Newton, and Cy is 3614.20 Newton. And then, okay, if you want to find out the shear force inside the pin, should I take Cx, Cy, or should I take both of them? How do I go with the component of the Cx? The total magnitude of C is responsible for the shear. Not only Cx, not only Cy, but you have to combine them. The magnitude, the total magnitude of the C that is responsible for the shear. So in that, I have to find the resultant of the C, that is the root value of Cx squared plus Cy squared. And that is okay. I have the value of FBD. Also, to find the value of force at C, I find a total resultant that is 4666.98 Newton. All right, now the question is giving me, yeah. So in shearing, the limit is 150 megapascal. So the shear stress of the failure So the nature of these forces are shearing stress. This is shearing force, and this one also is a shear force. So this is shear force at B, this is shear force at C. So this is actually two equations. If I take the first term with the 150, that gives me the diameter of B. If I take the second term with 150, that gives me the diameter of C. So easily you can solve that one and find the diameter for each. And in that, the diameter of pin B is 7.08 millimeter, and the diameter point pin at C, that is 6.29 millimeter. So that one is assuming someone a heavyweight person, I mean, 1,500, that is someone almost 150 kilograms. Someone 150 kilograms sitting on that, you need a pin of diameter of 6 millimeter. Anything thinner than that is going to cut. And with that, I'm assuming the pins are single shear. You know the difference between single shear and double shear? So double shear, the shear force develops over two areas. So here, that is a single shear. I mean, you could have made this double shear to become stronger. Double shear requires two tongues and one pin. But if that's one tongue, one pin, that's single shear. All right, now we have, I think, problem 11. That is kind of comprehensive. Let's see if we can take that question today. That would be it for now. So here, everything I did yesterday, that was calculation of the shearing stress or normal stress at one single point, internal force at single point. But if the problem is asking about variation of the internal forces, then you need to plot the shear force diagram, bending moment diagram, and that's the next question. Next question. Okay, so here, method of free body diagram is not useful. We have to use method of equation. Method of equation, the thing that most students confuse, that is method of equation always start from W. If you can't write the W for here, you can solve it. So that's the key for solving this problem. Now I try to get W of X. First of all, how many zones are here? Zones of loading. 2. One between A and C, one between C and B, zone of loading. Between X between 0 to 4.5, X between XA and XC. All right. Anyone can help me writing W of X. How do I write it? Back to the algebra. You want to find the equation of a line. You know how to find the equation of the line. Equation of a line in general term, that is AX plus B. Remember that? Or MX plus B something. How do I find A and B for a given scenario? By boundary conditions, by initial value. So initial value is W at X equal to 0. What is W that? Anyone? Nguyen, what is W at X equal to 0? Minus 50. Well done. Not 50, minus 50. That is where most of the students get it wrong. And if I plug that, this would be A times 0 plus B, and therefore B is equal to minus 50. How do I find A? That is X equal to 4.5. W of X is 0. W of 4.5 is equal to 0, right? That is A times 4.5 plus B, which is minus 50. That is equal to 0. Therefore, A is 50 divided by 4.5. That is 11.11. All right, all I need now is 11.11x minus 50. Everyone happy with that? So you easily can check this simply if I plug x equal to 0, that is minus 50. If I plug x equal to 4.5, that is also 0. Okay, what do I do next? Next, I know that dv, which is v of x, minus v of a. What is v of a? One step we skip, that was to calculate the reaction forces. So you have to find the reaction forces. If you solve the reaction forces, that is 112.5. So that is equal to integral of w dx between 0 and x. So that is v of x minus, so I know VA is equal to VB, that is equal to 112.5 kilonewton.
Explain the W part at the top, the WX.
WX.
Yeah, the one below.
All right, so that is, I went through calibration of the code. I assume with W of x be AX plus B. And then how do I find A and B? Simply at x equal to 0, W is equal to minus 50. At x equal to 4.5, W of x is 0. So you just apply those boundary conditions, initial values into AX plus B, and A and B are, A become 11.11, B become minus 50. So I just simply uh, summarize the result here. All right. So now I have to do the integration of W dx, which is what? That is 11.11 divided by 2 5.55 minus 50x. And then if I take that one to the other side, my shear force is 5.55 x squared minus 50x plus 11, that is in kilonewton. Is that clear? All right, so that I could start plotting. So at this stage, for the first zone, I can plot the v of x. So v of x at A, that is 112.5 kilonewton. And then this is a quadratic equation with a positive. So that's a cup pointing upward, and with the minimum being at here. So that is shear force becoming 0 here. Now, how do I find bending moment? What is bending moment at A? For T, what is bending moment at A? 0, because it's pin. Pin doesn't take any bending moment. So MA is equal to 0, is equal to MB, right? So now method of equation. Method of equation is telling me that dm over dx, that is equal to Vx. So therefore, m of x minus m of A so let me do the integration of the Vx. That is 185 x cubed minus 25 x squared plus so now the expression for m for the first zone, that is a cubic function. So that cubic function is maximum where the shear force is 0. And if I calculate m at 4.5, that becomes 169 kilonewton meter. Okay, the next step is we have to jump into the second zone. The second zone, yeah, I repeat the same steps. Just watch this one. Please note these steps. In the second zone, it is convenient to shift the coordinate system at C. So every zone, I bring the coordinate system right at the beginning of the zone to make the derivation easier. Okay, so now here I know that what is in the second zone, zone number 2. So here x again is changing between xc and xb, but bringing the coordinate at c, x would change between 0 to 4.5. That makes the derivation much easier. Now help me to find w of x for the second zone. So in this case, I assume my expression, this is a line, this is the equation of a line, okay? So that I would write this as cx plus d. How do I find c and d? What is w of x at x is 0? 0, well done. So w of 0 is equal to 0, that is c times 0 plus d. Therefore, d becomes 0. And how do I find d? That is w at 4.5. What is w of 4.5? Minus 50. Well done, Nguyen. And that is c times 4.5 is equal to minus 50. Therefore, c is equal to what? Minus 11.11. All right, minus 11. So if I write, let me summarize the result here. W of x is simply, for the second zone, that is the equation of a line minus 11.11 x. So how do I check that? X equal to 0, 0, X equal to 4.5. That is this is so V of C that is equal to 0. All right. All right, W of X is minus 11.11x. So V of C that is equal to 0, V of B that is minus 112.5. And how do I find V? So that is dV dx is equal to W of X, and therefore V of X minus V of C that is integral of X dx, that is, this is 0, V of X becomes minus 55.5 x squared. Okay, and if I plot that, this is a quadratic equation with a negative sign. That's a reverse cup, and the reverse cup has its maximum at here, so it goes like this one. So this is a cusp point right in the middle, the cusp. How do I go with the M? So this is just note, pay attention to this one. That is dm over dx is equal to V of X, and that gives me M of X minus M of C is equal to integral of minus 55.5 x2 dx. So what is M of C? What is M of C? From the left-hand side, M is 169, and there is no point bending moment, no discontinuity. It has to be discontinuous. So M of C is 169. So if I plug that here, my M of X is sorry, this is 5.55. And that, if I integrate that one more time, is minus 1.852 x cubed plus 169. And you easily can check this one. If you plug x equal to 0, that is 169. If you plug 4.5, this is 0. Okay, So that cubic function starts from this point and becomes 0 at this end here. All right, that was a relatively, doable problem if you follow the steps quickly. The challenge is you have to know what are the w of x as an expression. So from there, you just do 2-time integration. Careful about how you apply the boundary conditions and the beginnings. Anything else should be simple. So, all right, so now we have a few problems remain for tomorrow. Hopefully, we manage to complete them tomorrow. And all these recordings, I make them available. That's the best approach to get prepared for the exam. Any questions? Let me do the attendance for today. Okay, Sehrish is here, Natasha is here, Nguyen here, Chaisal away, Ahmad is here, Nijil here, Shah is here, Borth is here. Okay, any questions? Exam would be next Monday. We go to the BA building, the computer labs, very similar to the mid-semester test. There are Canvas quizzes, and just make sure you know. I will send you an announcement telling you how many questions, what are the markings. Yeah.
Question for quiz 2. Like I answered to part 4, 10.6. Where I got it from?
Well, I can't help you with Pearson. Pearson is absolutely handled by computers. They do the marking. I know that they have a very unusual graphic language. If you write this not according to what the computer expects, this is not marked by human, and that's done for everyone. So that's fair. Even if that's not perfect, everyone would be treated the same. Unfortunately, I can't help you, Pearson. But anything else, bring me questions to the tomorrow session. I will solve them for you.
Yeah, but can you open the quiz for me?
Okay, remind me, send me email. I
Email.
will open it for you.
Thank you.
Okay.